Alright, now we're going to take a look at using Multisim to help analyze a signal. Alright, so I've just drawn a basic circuit here using a signal source. It's operating at 60 hertz, 5 volts, so that's as high as that's going to get. Okay, I have a resistor and LED on here just so that you can watch and see that it's flashing on and off as it goes. This is the 4-channel oscilloscope. Okay, it can be found over here when you kind of hold your cursor over it. They're going to be over here. There's the 4-channel oscilloscope. So you'll just click on it and drag it over in the meantime when you do it. So the reason it was kind of faded out, I had the simulation on already. But I can come over here and I can grab the 4-channel oscilloscope and bring it on here. But it's right here. It's on channel A. Okay, so channel A is monitoring the output of this signal source right here. So let's go ahead and take a look at the simulation. So up here is the play button. Alright, and you're not going to see anything right away other than this LED flashing on and off. So in order to see the oscilloscope, you have to double click on the oscilloscope. So hopefully now you can see this going on my screen. You can see the signal as it's going on and off. I'm making a square wave. I'm down here, I'm notched on channel A, and I can reverse it. So if I like the black round back and want to see the red signal, or if I want to see the white signal, me personally, it's easier for me to see it in this aspect. Okay, I have the Y position here. I can change where this graph is showing. Alright, so by clicking on the little up and down arrows, I can toggle here. If I click down, notice the entire signal moves up or down. And I can sit here and change, I'm changing the Y position of the graph. Alright, so if I want to see it kind of like what we were learning in class, right? The time low here is on the x-axis and the time high is sitting right here at 5 volts. How do I know that's 5 volts? Right here on the scale underneath channel A it says 5 volts per division. Alright, so I can click inside here. I can change this and make this go up or down, and I'm going to shrink how the wavelength looks. Is the wavelength still the same? Yeah, so this is kind of like the example one we did. Alright, this is 2 volts per division. So each one of these boxes is 2 volts high. So right from here to here is 2 volts. Alright, and then from here to here is 2 volts, and then that's a half. Let me pause this for a second. So what we can see is it's constructing. Okay, so right now I have 2 volts per division in the Y direction. So that means this box is 2 volts high, 2 volts high, 2 volts high. So this signal is 2, 4, and then 1, because this box is 2 volts high and it's halfway through. So it's a total of 5 volts high. And I can verify that if I want to change this volts per division. I'm going to click down here and I'm going to make this 5 volts per division. So see how the box changes? Alright, so it's now 5 volts per box. And once again, if I can't see the time low, I can just change the Y position by clicking down here, and I'm going to move the signal up a little bit so I can see it. Alright, the x-axis down here doesn't have really anything to do with being negative or positive or things like that. Alright, so there's changing the axis. So I'm still on signal A. If I had a B, C, or D connected, I'd be able to swap them out. Alright, so let's figure out what the period of this. Also, I can scroll back and forth and look at the prior history of the signal, and I can catch up to here to where it's recording. Now, these are the markers we talked about in the first part of the lecture. I come over here and I left click and I can grab them. I'm going to put that first marker, I'm going to line it up right there. See how it changed colors? Means I'm right in line here, and then I'm going to grab the other marker over here and I'm going to place it right here. Well, what does this tell me? See how, got to make sure they're lined up. Alright, see how the markers are right here? What am I going for? I'm going for the period of this function. How long it takes to start from its starting point to return back to its starting point after it's gone through one complete cycle. So I'm using the markers. They show up right here where it says T2 minus T1. That's 16.69 milliseconds. Alright, so those markers are important. They're going to help you define the period. Alright, so you can only use them if you're using markers. Well, now, here's some verification. I want you to take, you can pause the video, grab your calculator real quick, but take this down here, this is the period, and we want to find the frequency. Frequency is 1 over the period. You cannot do 1 divided by 16. I mean, you can, but you got to know that that's in milliseconds, and you got to move the decimal. Or you can do 1 divided by parentheses 16.782, or sorry, 16.609 times 10 to the minus 3 close parentheses and hit enter. You should get approximately 60 hertz. Well, over here, that's the source signal frequency, 60 hertz, 5 volts. That's the amplitude of the waveform. All right, but this is how you can use the markers. Look, the marker will help me find out time high. I can move this marker here, and this is actually showing me time low, and I'll move the graph back down. So the x-axis here is the 0. This is showing me time low. Time low is the time the graph is down. So time low is 8.304 milliseconds. If I want to see time high, I'm going to move the marker over here and line it up-ish. I'll fix that one in a second. Alright, so we're going to line, for some reason, not as much fun to do this on a laptop. Alright, those are lined up close. That one's off a little bit, but this is 8.131 milliseconds. That's time high. That's how long the signal is sitting at 5 volts. So remember to do duty cycle. You're going to take this time, 8.131, divided by the period, which was approximately 16.609, I think, and then multiply by 100. That would give you the duty cycle. I can look at this and tell you the duty cycle is 50% anyways, or you got 8 over 16. It's 50% just because of how I have the signal set up. Alright, so I can drag these markers and move them out over here as well. I can also change the X scale. Right now, each one of these boxes down here, not the signal box, but a box down here that's on the grid, on the oscilloscope, that's 10 milliseconds long, which means each tick mark is 2 milliseconds. So 2, 4, 6, 8, 10. Alright, so this box length right here is 10 milliseconds. Now, I can change that. I can make it so it's 20. I can make it so it's 5 and maybe easier to see. I can shift the X position. So say maybe I want these lined up. I can shift them over just a little bit. I can keep changing the X position so that it lines up on a line so it's easier for me to calculate. Alright, but essentially, you know, that's using the oscilloscope and understanding the signal. So I'm going to back this back down to 0 here. And then what do we have this at? 10. 10 was nice and easy to see, and that was at 5 volts. So what I can do is I can stop. I can come back here. Alright, and let's change this signal here. Let's change this and make this 10 volts. Alright, so now when I simulate it, it's going to start over with a clean slate, and notice down here on my scale, it's 5 volts per division. So now that I'm running at 10 volts here, alright, each one of these boxes is 5 high. So this is 5 volts and then another 5 volts, so we can see the signal is now at, the amplitude of this signal is 10 volts. So the signal is now at 10 volts instead of 5. Alright, but every time you do this, you need to stop it and then come back and change, or it won't let you. So I'm going to change that signal back to 5, and then I want to show you the frequency change. Alright, so we're going to change the voltage back to 5 volts like it was. Alright, let's double this and see what happens. So now we're going to run at 120 hertz when we run this signal. So think about it. Should it be running faster or slower? Alright. If you said faster, good. Notice that these are happening much faster. Okay, they're a little bit, and it's still 10 milliseconds per division. It's just now it's happening more often than it was before.